Alright, well, welcome to geometry. This is the first section of the first chapter of the book. I'm going to talk about some things here that deal with that section, but before we do, I want to go over briefly what is this thing geometry and what do we do with it. All right, now geometry is the business of solving problems that deal with shapes and things. So say, for example, I want to know how tall a mountain is, but I can't actually, get out there with a tape measure and figure it out. Or maybe I'm trying to figure out, how big a lake is, but it's kind of an oblong shape and it's not real straightforward, right? These are sorts of problems I would solve using geometry. There's one catch, though. The catch is that all the tools that geometry has for us to solve problems like this are mathematical tools, which means they are ideas, they're formulas, they're equations, relationships between things. They're not things like hammers or measuring tape or anything like that we can actually take out into the real world. So all the tools we have in geometry aren't tools that we actually go into the real world with. They're only tools that we use in this sort of imaginary geometry world. And hopefully, when we use those tools in the imaginary geometry world, the answers that we get will work back in the real world. Let me show you an example. Let's say, for example, I have an aquarium. Here's my aquarium. And my aquarium it's full of water. It's my water here. And I want to know how much water is in my aquarium. Now I know that the volume of the aquarium is calculated as length and height. We could call this width. So I get my tape measure out and I measure this out. Now this is 24 inches. And now this is 10 inches, and this is 10 inches. So I go ahead and do my calculations and I get my volume. But notice that idea I use, that volume equals length times width times height. Now that's a geometric tool. And this length times width times height equals volume thing actually doesn't necessarily apply to this aquarium. It applies to a sort of imaginary box shape that only exists in the imaginary geometry world. In that imaginary geometry world, it's perfect. All the corners are perfect right angles. All the edges are perfect straight lines. The actual walls of the aquarium are infinitely thin. They meet at perfectly sharp corners. And that's not exactly what the real aquarium is like at all. The real aquarium sides might be bowed in a little bit. Could be a little rounded here at the corners. Maybe the thickness of the wall is thicker here than it is over here. So the answer I get by multiplying 24 times 10 times 10 is the volume of the sort of imaginary perfect aquarium, not the aquarium that I actually have sitting in my room. But hopefully, if everything goes well, my answer for the imaginary perfect aquarium is close enough to the real aquarium's volume for, my purposes. And that's how geometry works. A lot of the time, we're solving problems that deal with sort of imaginary perfect shapes and then trying to apply them to the real world. Which brings us to section 1. In section 1 of your textbook, we start out talking about points, lines, planes, segments, rays, and some other shapes like this. And these are some of the basic building blocks of all of those imaginary shapes, right? Imaginary perfect shapes. So that's what we're going to learn about in this section. Okay. So the first three things here are a point, a line, and a plane. A point has no dimensions, and a dimension is like length, width, and height on the aquarium. Point has none of those. It's just infinitely small. It's a tiny pinprick location in space somewhere. You hold out your finger, you're pointing at a point somewhere, right? Points are just infinitely small, imaginary actually. They're so perfectly small locations in space. Then we have lines. A line is, well, kind of what you would imagine a line being. It's just a straight line. And a straight line that travels, in this case, because it's an imaginary shape, it goes forever in both directions. Okay? And then we have a plane. And a plane is like a flat surface. And it's a flat surface that, even though we never draw it in these pictures like that, it's a flat surface that actually extends forever in all directions. Now, I want you to notice here it says that they are undefined terms, point, line, and plane. And we might come back to this later, this idea of undefined terms, but for now, it's perfectly alright if we just imagine point, line, and plane pretty much being what we think of them as being. So in our aquarium example, here's our aquarium, right? The points on the aquarium are like the corners of the aquarium. The lines are like the edges, and planes are like the faces, the sides of the aquarium. With, of course, the one exception that actually a plane would extend forever up and down, and the lines would sort of continue forever in these directions. What we're dealing with here in this aquarium example is actually more of a line segment, which we'll get to in a second. Alright, naming conventions, so that when we talk about these imaginary shapes we're drawing, we all know what we're talking about. Points, always named with capital letters. Typically you start with A, you move on to B, C, D, and so on. Lines. A line is named using the names of 2 points that are on the line, if you have 2 points labeled on the line. And when we do that, we put this, and maybe hard to see here, but that's a little double-headed arrow. I'm actually going to rewrite that over here. This is a line AB like such. So it has a double-headed arrow over top, and the double-headed arrow is kind of to signify that it's a line that goes forever in both directions. We could also, notice here, you could reverse them. Instead of AB, I could call it BA. It's the same thing, no problem. Now sometimes in a diagram, you won't have any points labeled on a line. In that case, they would just use a lowercase letter to represent the line and name the line. And I would write, if I were writing about this, I would call it line L. All right. Let's kind of take this away for a second. Let's move on down to the plane. Oh, wait, I would want to point this out. One of the reasons we need 2 point names. This is important. So let's say, for example, I just wanted to call this line A, right? Well, what if I had another line through here? How do I know which line I'm talking about? Is it the one I just drew, or is it the one that was already there? Or what about this one? Right? That one goes through A. Or what about this one here? That goes through A. All these lines go through A. So it doesn't make much sense to just call this line A. That would be confusing. However, if I call it line AB, well, there's only one line that goes through both A and B. So that's why we use 2 point names to label a line. See, now, moving on down to planes. A plane is named using 3, here I have this word down here I'm going to toss in. We have this word collinear, 3 non-collinear points. So let's see what we mean by that. The word collinear means all in a straight line. So for example, if I have several points like this, and they're all in a straight line together, they are collinear as a group. But if I toss one in here, the whole group together is no longer collinear because they're not all on the same line. So when we say collinear or not collinear, we're talking about a group of points. Either a group of points is yes, all on the same line like these are, or that group of points is not on the same line like these 3 are over here. So to name a plane, we're going to need 3 non-collinear points. For example, we could call this plane right here plane A, B, C. And the order you give them in doesn't matter. I call it BAC, CBA, whatever, it doesn't matter. Here's why we need 3 non-collinear points. If I just wanted to call it, say, for example, plane AB, right? Well, I could perhaps have another plane right here, a flat surface that also passes through AB. And I don't know which one I'm talking about. Is it the one I just drew here, or is it over here? So I need that third point C. And it's important that that third point C not be collinear in a straight line, because if it were, imagine I had a point here called D, and I called this plane ABD, I still have the same problem where this extra plane also goes, the blue one here, also goes through the 3 points in the middle, just like the other plane does. So I don't know which one I'm talking about. It's the flat plane or the upright one, if I call it BDA. So it has to be 3 non-collinear points, right, in order to name a plane, so that there's no confusion about what it is that you're talking about. Speaking of collinear, there's another term here called coplanar. Coplanar means all on the same plane or all on the same flat surface. And I do want to give you a heads up about 2 kind of trick questions that may come up. One is, you may be asked if points A and B are collinear. Or for example, let's pick over ones over here. I'd pick like S and V. Are S and V collinear? Well, you're going to look at this diagram and you say, well, there's no line going through these. They're not on the same line. But the answer, and it's kind of cheap, I think, but is that I could draw a line that went through S and V. So they're on the same line. They're possibly on the same line together. But if I said S and V and say P over here, there's no way to draw a line that goes through S, V, and P. It just wouldn't happen. So those 3 points are not collinear or non-collinear. So if you're ever asked if any 2 points are collinear, the answer is always yes. Along the same lines, coplanar, you may be asked if any 3 points are coplanar. So for example, Q, P, and S, are they coplanar? Well, if you look at them, you'd say, first I'd say, well, no, they're not coplanar, because there's the plane down here and Q's not in the plane, so not coplanar. But the truth is, you could take any 3 points in space and you could always sort of, and it'd be hard for me to draw this, but you could always kind of lay a flat surface like a board so that it touched all 3 points. Here's an interesting little bit that goes with that. If you've ever seen a three-legged stool, three-legged stools always sit flat because they have 3 points, and you can always find a flat surface that'll rest on those 3 points. So a three-legged stool never rocks back and forth, unlike a four-legged stool, where it's possible that no matter how you sit the stool, the 4 aren't always going to be on the same plane. They are not coplanar or non-coplanar. Well, anyway, so any 3 points, you could always lay a flat surface against them, and so we would always consider them to be coplanar. And again, the word coplanar, just like the word collinear, refers to a group of points. So for example, S, P, Q, and then I toss in V, now they are not coplanar. The group as a whole is not coplanar because there's no way to make a flat surface touch all 4 of those points. Alright, let's take a look at some examples here. It says, give 2 other names for line PQ, notice the double-headed arrow, line PQ, and plane R. So if we look here, there's point P, there's point Q, so the line PQ is this line right here. If we wanted to give it a different name, we could call it QP. Remember, we could just reverse the letters in the name. You'll also notice that they put this lowercase n up here, so I could call it line N as well. We would just write it out that way. Next it says, name 3 points that are collinear. So let's take a look here. Well, I've got S and P and T, and those are all collinear in a straight line. Next, it asks for, let's see, 4 points that are coplanar. 4 points that are coplanar. Well, if we look here, they've got this flat surface that they've drawn in, and S, P, T, and V are all coplanar. Okay, next up we have segments and rays. So a couple things that are kind of like lines, but not quite. A segment, illustrated here, is like a part of a line. So it travels from one endpoint to the other endpoint, but it definitely ends there. It does not travel on forever like a line does. So in this case, we could call this segment A, B, and we would put a line over top of it, but with no arrows. And that tells us that it's a segment. It does not go on forever in either direction. We could also reverse the letters there and call it BA. And we'd be talking about the same thing. It doesn't matter what order I put them in. Next, we have a ray. If you look at the ray here, a ray is also like a part of a line, except it's cut off over here. Point A is a starting point, which is sometimes called an initial point, or more commonly just called an end point. So this ray here starts at A, travels through B, and then continues on forever. And in that case, we would call that ray AB, and we would put a single arrow. And the arrow that we draw, notice how it starts at A and it travels through B over here. One thing to watch out for, this is a pretty common mistake, if I say ray BA, right, we can reverse, for lines and segments, we can just reverse the names, and that's totally fair. But here, notice ray BA starts at B and travels through A, whereas AB starts at A and travels through B. So they start at different places and they go in different directions. These two are not the same ray. You can't just reverse the letters and the names. A couple little things about, one little thing about rays here, we've got this idea of opposite rays. And opposite rays are rays that travel. They start at the same point and travel in opposite directions. So here I could talk about ray CB, which starts at C and travels through B. On the other hand, I could talk about ray CA, which starts at C and travels through A. And these are opposite rays because they both start at C, right, but they travel in opposite directions, completely opposite directions. By the way, just a little side note, the arrow in the ray symbol always travels to the left. So you would never write down, for example, if I want to have like BA here, I would never write AB and draw the ray sign in the other direction. That's just a no-no. We don't do that. So I want to make a couple little side comments here. If I have a line that has several points on it, all right, say A, B, C, okay, it would be perfectly okay in this situation to talk about ray BC. There's a ray that starts at B, travels through C, and goes on in this direction forever. So we could talk about ray BC. Even though there's stuff over here, that's no big deal. Ray BC still exists. Right? It's just maybe a little hard to see because it's not colored in with a separate color. Right? It'll be perfectly okay to talk about it. Also, a ray BC, if I had another point in here, say, I don't know, put here, we'll call it D, it would also be okay for me to call this ray BD. So this ray BD and ray BC are the same ray. They both start at B, right here at B, and they both travel in the same direction and go through all the same places. It's just that I picked a different point to tell people what direction it's going in. So here I pick C, here I pick D, but since they're all collinear on the same line together and going in the same direction, these are the same thing, the same ray right here. So you'll sometimes be asked to find a different name for a ray. Look for another point that's on that same line to use as your second point in the ray name. Similarly, along the same lines, it would be okay to talk about segment AB. Sure, there's stuff over here and there's stuff over here, but that doesn't mean that there isn't a segment AB. There's definitely a segment AB here. Like I said, you could talk about it because I'm talking about just the places from A to B, the stuff in the middle. All right, so I could talk about that, and it would be appropriate to say that again, even though you see in the diagram stuff going on further on both sides. Alright, so quick example here. They want us to give another name for GH. It's segment GH. So let's see, there's G, there's H. So it's a segment. I can just reverse the letters. So I could call this HG, segment HG, and that'd be perfectly okay. Alright, next it wants us to name all the rays with endpoint J. So let's start with that. Let's see, we have, well, JF, we have JH, we have JE, and we've got JG. Okay. It also says here which of these rays are opposite rays, and if you look here, clearly the red ray and the green ray are opposite rays. They both start at the same place, travel in opposite directions, and the blue ray and the yellow ray also start at the same place and go in opposite directions. Remember, when we talk about opposite rays, we're talking about a relationship between a pair of rays. So I would never say that, oh, JH is an opposite ray. No, you have to have two of them to be opposites. Okay? Next, we're going to talk about sketching intersections. The word intersection itself is something you should be aware of. Intersection is just all the points that two shapes share in common. So for example, this line here, line M, crosses line N, and they both meet at point A, so they share point A. That is their intersection. Or here, I've got these two planes, the vertical plane and this horizontal plane, and they share this line in the middle, line Q. So line Q is their intersection. And this is, down here, we've got some valuable stuff to look at in terms of, what types of intersections shapes can have. The sketching part, I don't want you to stress yourself out about. You don't have to be a great artist to do geometry, but I'm going to point a couple things out here. Here they talk about lines and planes. There are three different ways that a line can intersect a plane. In this example, the line is actually in the plane, so every point that's on the line is also in the plane. So we would say that the intersection of the line and the plane is actually the whole line. Here, the line is sort of floating above the plane, and presumably it's kind of parallel to it, so it's not at some point in its forever journey going to cross the plane, and so it's never going to touch it. They don't share any points in common at all, so the intersection is nothing. It's empty. Here, we have a line sort of piercing the plane, kind of like an arrow going through the plane, so they meet just at a single point right here. And so that one point where they meet is their intersection. And then I think down below they talk about how to draw these things, which is kind of nonsense, but I will draw a couple of them for you real quick here. Alright, it says sketch a plane in a line that is in the plane. So I'll just kind of, here's my plane, and here's my line that's in the plane, going in both directions. Done. Next it says sketch a plane in a line that does not intersect the plane. So I'm just kind of drawing this. Here I'll pick a different color. Here I've got my plane again, and then here's my line above the plane. These are terrible drawings, but there you go. And then last but not least, it says sketch a plane in a line that intersects a plane at a point. So I would kind of draw, here's my plane, and then my line goes, I might draw the point there and then continues on. Maybe I'll label that point A and make sure that my line goes in both directions. Okay? Point A there, right? Then we're done with that. Don't worry about this stuff. I'm never going to really ask you to sketch things like this. We don't have to be artists to be good with geometry. Next it says sketch two planes that intersect in a line. So I guess I'll do that for you. Here is one plane, sort of flat surface there. And then in a different color, I'm going to kind of sketch the line in first. So I can go whoop. There, kind of like that. So again, terrible drawing. There's the line that they share in common. They don't have to be at 90-degree angles like this looks either. It could be any sort of angle. It would be the same deal. Any two planes, if they do intersect, if they do cross each other, they always cross each other and they share a line together somewhere. You could think of, for example, that aquarium we looked at earlier, right? Here is the front of the aquarium represents a plane, and the top of the aquarium represents a plane, and the place where they meet is a straight line. So, and then the sides of the aquarium, the top of the aquarium, so on. Every time one of the two faces of the aquarium, they're all could be represented by planes. Anytime they meet in a straight line. Moving on. All right, last, we're going to take a look at this sort of quote-unquote real-life problem here. So get a little closer to it here. Okay, so it says that we have, the diagram shows a molecule of sulfur hexafluoride, the most potent greenhouse gas in the world. Name two different planes that contain line R. So let's find line R here. I see my R over there. So this must be line R. So I'm trying to find two planes that contain line R. Now remember, to name a plane, I need three non-collinear points, 3 points that are not in a straight line. So I see I've got a couple of points here. I've got D and F that are on that line. I've also got B on that line. So if I want to pick a point that's going to help me name a plane, I have to pick something that is, I can't pick all 3 points on this line, but I could pick 2 on this line, and that'd be a good idea, because then if I know I've got, say, F and I've got, say, D, I've also got B in there. So we're going to call this plane D, F, and then I need to pick a point that is not in that same line, so I could pick, say, A up here. And notice that what I'd be picking is this vertical plane that goes through here. Now, pick a second plane that also has that in there. So it could also have point D and point F, so we'll start with D and F. But this time, I don't want that same vertical plane, so obviously I'm not going to pick A again, but I also don't want to pick C, because then I'd be kind of picking the same plane. I'd just be giving 2 different names for the same plane. So instead, I'll pick, say, G out here, right? And now I'm picking this sort of horizontal plane that goes through here. So 2 different planes that both contain that line. All right, now if you look here in your student journal, you'll see that a lot of the stuff that we just talked about is kind of recorded here, so you got that for your reference. So we've got note-taking and vocabulary. So there's more problems here. So what you could do, if you'd like to, is go ahead and practice these problems, and then I'll pause the video, practice them, then come back, and I'll quickly give you some answers for these. And then on the other hand, you could just skip them if you feel really confident about this. I guess just stop the video now. But, all right, so pause the video and then come back. Okay. Okay. So let's take a look here. See, we've got, see, give 2 other names for CD. I think this is line CD. So there's C and there's D. First thing I could do is I could reverse, and I could call this DC. Or since it's got this little M here, I could call it line M. Right? That would be okay. Next it says, let's see, give another name for plane M. There's the M down here. I could name it with 3 non-collinear points. So I could call it plane A, C, and say E, because those 3 aren't in a straight line together. A, C, E. Let's see, next it says, name 3 points that are collinear. Okay. A and C and B are all collinear. Next it says name a 4th point that's not collinear. I could pick, say, E, or I could also pick D. In any case, remember, the group altogether is not collinear. Right? So the first group, ACB, that group is collinear, all on the same line. If I toss in D, the group ACB and D all together, not collinear anymore because they're not all on the straight line together. All right, next we've got what is another name for PQ. Let's see, I've got P and I've got Q. It's the line PQ. So I could just reverse them and say QP with the double-headed arrow over top to say that it's a line. Next it says, what's another name for RS? I think it's kind of hard for me to tell there. I think it's segment RS. But you can probably figure it out if I've got that a little bit wrong. So for RS, I could just, there's R, there's S. I could call this line K. By the way, I guess I could have called this line J over here as well. Or I could just reverse the letters and call it S, R, and be done with it. Okay, next up it says, name all rays with endpoint T. So I'm going to zoom in here just a little bit. Endpoint T. So let's take a look. We have TR. We have TQ. We have TS. Oop, my handwriting's terrible. And we have TP. And we talk about which ones are opposite rays. Well, clearly the red and green rays start at the same point, go in opposite directions, and they are opposite rays. And the blue ray and the yellow ray are also start at the same point, T, and go in opposite directions. So they are opposite rays. Okay, next it says, on the diagram, draw, we're going to skip that. If you want to, you could try and draw the two planes in. I'm not too worried about it. Here, it says, sketch the figures described, AB and BC. So let's see, we could just do, here's A, B, and C. So I really don't have to do anything more than that. I could draw some arrows in to say it's a line, but there is a segment from A to B. There is a segment from B to C. Here it says line K in plane M. So here's plane M, and I could draw line K in the middle there, and I'd be done. All right. Thank you for listening. This has been a lot of talking here. All right, I'm done.